We are starting part B of the module 3 today, and in this part B we are going to look at the analysis of discretized equations. The idea being that as shown in the last case study, not every finite difference approximation for every derivative gives us a solution which is satisfactory. So, we would like to see under what conditions we get a proper solution and how to solve these equations properly. This analysis is essentially in two parts. In the first part, we try to answer the question, given a discretization scheme, how to tell that this scheme consisting of the specific approximations that we make for the derivatives that appear in the governing equation, okay, that particular scheme will lead us to a satisfactory solution. So, this is a question that we will address in this module, but there is also the analysis of the numerical schemes answering a different question, that is how to solve together the set of continuity, momentum, energy equation and other equations, and that is going to be done in the next module. So, that is module 4. So, as far as this part B of the module is concerned, we are going to look at one equation, and it is like the scalar transport equation, and in fact the elements of those equations, to come up with the methodology for analyzing a given discretization scheme and telling a priori whether it is going to give us a reasonably satisfactory solution. So, that is what we are going to do in part B of this basic concepts of CFD. In part A, what we have seen is that we have seen the derivation of the finite difference approximations for any derivative to any order of accuracy that is desired. And as part of this derivation, we have seen that for a given derivative there are a number of approximations are possible, and when you have number of such derivatives that appear, there can be number of possible schemes by which the overall partial differential equation can be converted to an algebraic equation at a particular space and time location, and this can be applied for all the points at which we want to have a solution, and we can have a set of equations which will then be used to find the solution. Okay. The questions that we wanted to answer were that are all the discretizations equivalent, and are there some discretizations that are superior, and how can we tell that we will have a numerical solution which is correct. And we try to answer these questions by taking a simple case of linear convection equation or the linear wave equation, dou u by dou t plus a dou u by dou x equal to 0, and we considered the explicit difference schemes, the forward in time, backward in space, forward in time, central in space, and forward in time, forward in space, and we expressed the discretized equation in the as a function of the parameter Courant number sigma, which is given by a delta t by delta x, and since these are all explicit methods, we can march forward in time and space. And what we are expecting was that for a given initial condition where f(x) equal to 1 over an interval from x equal to 0.1 to 0.2 and 0 everywhere else, we are expecting that this rectangular pulse to be carried forward in the x direction as time progresses at a speed of 1 meter per second. Okay. And then we compared the solution at different time at a fixed time of 0.1 second using different schemes like the FTBS, FTFS and FTCS, and using different values of Courant number. So, that is for a given delta x we simply varied the delta t, and we were expecting certain trend to be reflected in the solution. For example, if you take a specific scheme like FTBS, and then if you were to reduce the Courant number that is reduce the delta t, we are expecting more accurate solution. We are not really getting that. And if you were to increase delta t, Courant number, we are expecting again probably because of larger accuracy, larger discretization error as delta t increases, we are expecting slightly worse result than what we would be getting with a certain value of Courant number. And we are finding that when Courant number goes beyond a certain limit, it seems to be giving us very odd, unacceptable results, unstable results. And we find that FT-CS scheme, which is supposed to be more accurate at least for the space derivative than the backward in space scheme, was actually giving very wrong results even for the Courant numbers in which the FT-BS scheme gave somewhat good results, acceptable results. And for the FT-FS scheme, we found that although it is formally of the same order of accuracy in terms of accuracy of the same order as the FT-BS scheme, it was giving no good solution for any value of Courant number. Okay, so this is the kind of specificity of the solution, sensitivity of the solution to the scheme that we use and to the value of delta t and delta x that we employ, that is surprising, and it is also in a way intimidating, because we do not know which ones to choose. Okay, how do we know that we have chosen the right kind of values, and how can we trust the solution when it is exhibiting this sort of erratic behavior. So that is essentially why we need to have an analysis of a given discretization scheme, so as to see that it would actually give us a proper solution. So here, when we look at the analysis, we notice that our solution, CFD solution, is done in stages. That is, we first convert the partial differential equation to a discretized equation, and then we solve the discretized equation. We do not solve the partial differential equation. So the solution is obtained in two steps. One is the converting the PD into a discretized algebraic equation, and then solving the set of algebraic equations in order to get a solution. Okay. So if we want convergence, so where we define convergence as the computed solution must be the same as the exact solution in the limiting case. Why in the limiting case? Because we know that we are making approximations of the derivatives, and these approximations involve truncation errors of the order of delta x or delta x square or delta x cube, like that, and similarly for delta t. So in the limiting case, if the delta t and delta x go to 0, that is for very fine grids, we can expect convergence between the computed solution and the exact solution of the partial differential equation. So in order to get convergence, we would have to have consistency, which is that the discretized equation that we are solving, that we are approximating the partial differential equation, so that must be a mirror reflection, okay, or it must be the same as the partial differential equation in the limiting case. That must be one condition, so that we can say that we are solving the correct equation and not some approximate form which leads to a different kind of approximation than what is there in the partial differential equation. And secondly, that the discretized equation that we are solving must reach the exact solution of the discretized equation and not some approximation or a solution which is not intended to be there, okay, which is the which is known as a stability condition. So that is that in order to get convergence of the convergence between the CFD solution and the exact solution of the partial differential equation, we need to ensure that we have consistency, which is that the discretized equation which we are solving is the same as the partial differential equation which we are supposed to solve in the limiting case of delta t and delta x tending to 0, and secondly the discretized equation that we are solving using certain time stepping, okay, using certain delta x stepping. Okay. In the process of doing this discretized solution, which is a computed solution which has finite precision arithmetic, okay, in the process of doing this we do not expect the errors to build up through the successive mathematical operations that we undertake in order to get to the solution. So, there is a possibility of build up when you do repeated mathematical operations like addition, subtraction, multiplication and division, and if you do many of those, and if at every step, because you have finite precision arithmetic, so that means that when you add 2 plus 2 it is not exactly equal to 4, it may be 3.99999 something, there is a small difference that may be there. Okay. So, the difference in every mathematical operation that you carry out, we would like them not to add up and to build up so as to compromise the computed solution. So, that is a stability aspect. So, if you have consistency and if you have stability and if you have a linear equation, there is an equivalence theorem of Lax proposed by Lax, which is that for a well posed linear initial value problem with a consistent discretization, stability is the necessary and sufficient condition for convergence. So, this is a very useful theorem for us to have, so that convergence can be achieved for a certain mathematical problem, which is that it is a linear initial value problem with well posed boundary conditions. Okay, it is a well posed mathematical problem. If you have a well posed mathematical problem and if you have a discretization which is consistent in the sense that the truncation error between the involved in the discretization goes to 0 as the delta t and delta x and other terms go to 0, other parameters go to 0, and if you also have stability, that is in the sense that errors from whatever source that we are that are present, either from the boundary conditions or from approximations made in different derivatives of the equation, okay, or in the round off errors, all these errors do not build up so as to give rise to a bad solution. Okay. So, if that stability of the computation is guaranteed, then we can expect to get a convergence of the computed solution towards the exact solution in the limiting case of delta t and delta x tending to 0. So, that is, if we keep on finding a better and better solution, okay, a newer and newer solution for delta t and delta x becoming smaller and smaller. So, that is, you take a certain delta a grid computational domain of say length L, and then you divide it into 10 parts and you get a solution, you get a time dependent solution, and you use a delta t of say 1 second, and then you march forward for 10 seconds and you get a solution at the end of 10 seconds over this domain between 0 and L. Now, you do the same thing, that is solution at the end of 10 seconds, now with 20 grids in the same length of between 0 and L, and you use 20 time steps to get there, so that your delta t is smaller and delta x is smaller. Now, you get a different solution, and then instead of now using 20 cells, maybe you use 50 cells and maybe you use 100 time steps to reach there, you get a solution. So, as you keep on decreasing the grid spacing in both space delta x and time delta t, you will be getting a solution which supposedly has lesser and lesser truncation error. Okay. Now, if the scheme is stable, then we expect to get a solution which is better and better in such a way that for very fine delta x and very fine very small delta t, we can expect our computed solution to match with the exact solution of the partial differential equation. So, that is what we mean by convergence, that when we have very small delta x and very small delta t, if convergence is guaranteed, then we know that we are getting a solution which would match with the exact solution. Okay. So, convergence assures us that a grid independent solution, that is a solution which does not effectively change with further decrease in delta x, because we have probably reached the limit of variation there in terms of the gradients that are present and in terms of the accuracy of the computer and all that. So, in such a case we can expect the exact solution to match with the converged solution, but it is not necessary that the solution that we are testing is equally sensitive to all changes in delta x and delta t. Okay. So, for example, if we solve for the temperature variation and deduce from that a heat transfer coefficient, the heat transfer coefficient is obtained from the gradient at the boundaries. So, the gradient at the boundaries may be either less sensitive or more sensitive than the temperature at a particular location within the domain. Okay. So, we have to be clear about this, that we are solving, for example, in a heat transfer problem, we are solving for temperature, and from that we are deducing the heat transfer coefficient. Okay. The heat transfer coefficient is determined by the gradients at the boundaries, and temperature is determined by the corresponding temperature equation, energy balance equation, and it has many more terms and it has a variation which is different at different points within the domain. So, for example, if you are monitoring the maximum temperature in the domain, it may be less sensitive than the gradient at a particular location, okay, at a particular location at the wall. And if you are looking at the average gradient, so that you can get the average heat transfer coefficient, the average heat transfer coefficient is going to be less sensitive than the gradient at a particular location. So, in that sense, if you have a monitoring point at which you look at how the solution is evolving, then the solution at the monitoring point may be more sensitive or less sensitive than the final solution that we would like to have. For example, in a case of flow through a duct, then we specify a pressure gradient and we try to get the average velocity. Okay. Or you specify an average velocity, we expect to get the mean maximum velocity and the pressure gradient. So, if you are looking at these bulk quantities, like what is the overall pressure gradient for a given flow rate, okay, or what is the overall flow rate for a given pressure gradient, or what is the overall heat transfer coefficient for a given heat flux or flow rate or for given temperature boundary conditions. So, we are talking about overall values. So, these overall values do not exhibit the same sensitivity as a solution, as part of the solution, for example, temperature at a particular point, or the velocity at a particular point, or the maximum velocity or the maximum gradient. So, these things are going to be different. So, we have to keep this in mind when we talk about convergence, because when we talk about convergence and grid independence, we are looking at some parameter, maybe the average heat transfer coefficient or gradient at a particular location or the maximum value of the velocity, and we are seeing whether this parameter, this value here is going to change as I decrease my delta x and decrease my delta t. And when we find that if you further and further decrease the delta x, this value is not changing, then we say that we have convergence, we have a grid independent solution. Okay. Now, whether the grid independent solution is convergent with the exact solution of the partial differential equation is something that depends on the consistency and stability, and it also depends on whether the solution that you are comparing is the same as the problem that you are solving. Okay. For example, when you are looking at, if you say that you are looking at the maximum velocity, the velocity at a particular point, okay, that point is obtained from the partial differential equation. But if you say that you are looking at a gradient at a particular wall location, so then that is not necessarily given by the partial differential equation, it is given partly by the partial differential equation and partly by the boundary condition. So, the errors in the way that you use the boundary conditions and errors in the way that you are discretizing the partial differential equation, they both come into picture and it is slightly different. So, these complications are there when you are doing a practical problem, but let us just say from a purely conceptual point of view that if you can demonstrate that the equation that you are solving is an exact match of the partial differential equation, and if you can show that your numerical solution of the discretized equation is stable to small perturbations, small errors that may be coming from different values of different terms at different points of solution. Okay. If you can show that it is stable and its errors do not build up, perturbations do not build up and give rise to instability, then you can hope to get a converged solution in the limiting case of delta t and delta x tending to 0. Okay. So, this is the way that we can ensure that we have a discretized scheme involving certain approximations for all the derivatives that that are present in an equation. Okay. That discretization scheme is going to give us a reasonably accurate solution. So, we are saying that in order to, for example, in order to get a proper solution with the FTBS scheme or FTCS scheme or FTFS scheme, we need to have two conditions. Firstly, that the FTBS scheme that we have here, this particular approximation, this particular way of getting ui n plus 1 is such that this scheme approaches the exact solution in the limiting case, because at this stage we only have a proposal for a scheme as to how we can get ui at n plus 1. We have not actually implemented it. Okay. So, we are claiming that at this stage that these two differ only by the truncation error. Okay. So, if the error between the equation that you are solving and the equation that you are supposed to solve goes to 0 as delta t and delta x tend to 0, then you can claim consistency condition, okay, that you have a consistent discretization. So, if the discretization of this equation is consistent, so for example, if FTBS equation is a discretization scheme is consistent, then that means that the difference between this equation and this equation, which is essentially arising from the truncation errors, from the approximations that you have made in taking the first two terms in the Taylor series expansion of this gradient, and similarly the truncation error that you made in this. So, the sum of all these truncation errors, the cumulative effect of all these truncation errors is such that it tends to 0 as delta t and delta x tend to 0. So, once you can make that claim, you can say that you have a consistent discretization. So, the first question that we would like to answer is the FTBS scheme consistent? Similarly, is the FTCS scheme consistent, and if the FTFS scheme consistent? If one of these schemes, if a specific scheme is consistent, then the next question that we will have to answer is that is the solution stable? So, that is, we are starting with some n equal to 0 values, some initial condition here, and then we are getting ui at n plus 1 at a particular point, and then we are skipping to the next space point and then next point. So, we march from point to point and then we go up to all the points at a particular time step level and then we move on to it. So, that means that we have a solution at ui at n plus 1, for example at the 9th point and at 10th time step, which depends on the previous time step values, and the previous time step values depend on the previous time step values and so on. So, that means that in the process of coming to the 10th spatial point, 9th spatial point at the 10th spatial time step, you have built up, you have accumulated the error that you made at the previous time step and at the neighboring locations, and then at the previous time step of those things at the 8th time step of the 9th grid point and then the 10th grid point and 8th grid point, like that. So, all those errors that you made at previous time steps, have they died down or are they accumulating? Okay, are they accumulating to such an extent that these perturbations will build up and make your solution unstable? So, that is a stability part that we would like to demonstrate. So, if we can show, if we can demonstrate that the FTBS scheme is both consistent and stable, then we can expect that the solution that we get by following through with this FTBS scheme is going to be a convergent solution. Okay. Similarly, with the FTCS scheme and FTFS scheme, or with any other way of approximating the derivatives, because these are only 3 different ways. There can be a second order approximation in the time derivative, there can be a third order accurate approximation in the space derivative, they can be implicit, they can be explicit, there can be many combinations. For any combination that we make, for any numerical scheme that we propose, for example this or this or this, to find the solution, we need to satisfy the consistency condition and the stability condition. If we do that, then we can hope to get a converged solution. So, in the next lecture, we are going to look at how to verify the consistency of a given discretization scheme, and we will also see how to verify the stability of a given discretization scheme. If we can come up with some generic methods for doing this analysis, then we will be able to do this analysis for a given discretization scheme and see whether it satisfies both the conditions. If it satisfies both the conditions, then we can go ahead and get solution. If it does not satisfy either of these conditions, then we have no guarantee that the computed solution is going to be good. We will say that we will not use this scheme, we will use some other method to do this. So, that is the idea of this analysis, which is what we are going to do in the next couple of lectures.